So having revised our understanding of indices, both positive and negative, we can now have a look at scientific notation. So scientific notation is used to express very large or very small numbers, okay? And the numbers of that kind of magnitude come about a lot in science, and so hence it's used frequently in science. In maths, to be honest, we don't ever tend, well, unless, yeah, in certain situations possibly, but we don't really tend to represent numbers using scientific notation, but it's really common in your science subjects. Okay, so scientific notation involves using powers of 10, and powers of 10 are useful due to the decimal nature of our number system. In our number system, each digit is essentially a power of 10, okay? It's a if we are multiplying numbers by 10, we know that we can simply add a 0 onto the end, or if it's a decimal value, we move the decimal point one place to the right, which is essentially what we're doing. So if we have 73 and we multiply that by 10, the decimal point is currently here, and so we move the decimal point one place to the right, and instead we get 730 when we multiply it by 10. If the number is 7.3 and we multiply it by 10, we move the decimal point one place to the right, and we get 73. If the number is 0.73 and we want to multiply it by 10, we move the decimal point one place to the right and we get 7.3. The same is true of dividing, obviously. If the number is 64 and we want to divide it by 10, the decimal point is currently here and we move it one place to the left, so it becomes 6.4. If the number is 6.4 and we want to divide it by 10, we move the decimal point one place to the left and it becomes 0.64. So multiplying and dividing by 10 is very easy in our decimal system because it simply requires changing the place value of each digit. Okay, if we've got 234, when you divide by 10, this was a units digit and it now becomes tenths digit. This was a tens digit and it now becomes a units digit. This was a hundreds digit and it now becomes a tens digit. So we're simply changing the place value of each digit by a factor of 10. Okay, so for example, if we've got this number here, okay, what's that going to be? A lot, 126 billion, depending on the way you define billion. It's different in America and in the UK. I'm not interested in the size of the number, I'm interested in how to represent it in scientific notation. So for example, 126 with 9 zeros after it is 126 times 1 with 9 zeros after it. And 1 with 9 zeros after it is 10 to the power of 9, okay? And so we could write 126 with 9 zeros as 126 times 10 to the power of 9. Now, it's conventional to write scientific notation in this form, a number times 10 to the power of a number, where this number at the beginning, is somewhere between 1 and 10. So actually, this is not technically in scientific notation because 126 is not between 1 and 10. Sorry, I've just seen a typo there too. That should be integer, not integer. So integer being positive or negative, sorry, can't speak and write at the same time. Integer being a positive or negative whole number, okay? So it can't be a fractional or a decimal up there. So 10 to the power of an integer, positive or negative whole number. And this number, should be between 1 and 10, inclusive of 1 but less than 10. So that means where we wrote this number as 126 times 10 to the power of 9, 126 isn't between 1 and 10. We would need to write that as 1.26 instead. Now 126 is 1.26 times 10 squared. Okay, and so therefore actually instead of writing it as 126 times 10 to the power of 9, we need to write it as 1.26 times 10 to the power of, we group that 10 squared together with the 10 to the 9, and we get 10 to the power of 11. So this number in scientific notation is 1.26 times 10 to the power of 11, meaning we take this decimal point from here and we move it to the right 11 times. So moving it to the right twice will get us to 126, and then a further 9 will add 9 zeros onto the end of 126. So for very small numbers, we're dividing by a power of 10. Okay, so we can express this, rather than dividing by a power of 10, we can express this as multiplying by a negative power of 10. Okay, so for example, 0.0000123 is 1.23 divided by 10 to the power of 5. So if we need to 1, 2, 3, 4, 5. The decimal point is going to need to go there for the number to be between 1 and 10, 1.23, and in doing that we've moved the decimal point 5 places. So we're going to need to take 1.23 and then further divide it, so move the decimal point 1, 2, 3, 4, 5 to the left to make it 0.0000123. So we need to divide by 10 to the power of 5, which is the same as multiplying by 1 over 10 to the power of 5, and 1 over 10 to the power of 5 is 10 to the negative 5. So rather than dividing by 10 to the 5, we write it as multiplying by 10 to the negative 5. Okay, so for example, express each of the following in scientific notation. So the first step is to take the non-zero digits, okay? Now, if there's a 0, so it doesn't mean that 507 becomes 57. We can't ignore any zeros that happen between the first and the last non-zero digit. So I'm going to write down those digits, 507. They're what we would call the significant figures of this number. And I need to put the decimal point so that that's a number between 1 and 10. So it's going to have to be 5.07. So if I'm moving the decimal point here, I'm going to then need to multiply by 10, 1, 2, 3, 4, 5, 6 times to make these things equal, times by 10 to the power of 6. Alright, this one here, the 6 threes are what we call the significant figures, 6, 3, and then I need to place the decimal place so it's between 1 and 10, so it's going to have to be 6.3. So if I need the decimal point to go here, I'm going to need to divide by 10, 1, 2, 3, 4, 5, 6 times to make it the same as this. So multiply by 10 to the power of negative 6 to divide by 10 6 times. Express each of the following as a basic numeral. Basic numerals is a slightly vague term. Essentially we want to write it not in scientific notation. So 5.4 times 10 to the 3 means multiplying by 10 3 times. Multiplying by 10 once will make it 54. Twice will be 540. 3 times will be 5,400. Okay. 1.33 times 10 to the negative 6, so we want to divide by 10 6 times. So dividing by 10 once is going to be 0.133, and so then we need to divide by 10 5 further times, so it's going to need to be 5 zeros in front of that. So it's going to be 0.12345 and then 133. Okay, so we can check if the decimal point's here. 1, 2, 3, 4, 5, 6. Yeah. Okay. Now this 0 doesn't count as one of those zeros. That's just a conventional thing because we don't like to just write point something because it's really easy for the dot to just get lost. Oh, is that just a mark on the page? So we always write 0 point something, but this has not got any significance in terms of the value of the number. Alright, so I've made reference to significant figures. So in any number, the first significant figure is the first non-zero digit in the number. And then every digit between the first non-zero digit and the last non-zero digit is considered significant. So here where we've got the number 507,600, it has 4 significant figures because the first non-zero digit is 5, the last non-zero digit is 6, and everything between those counts as significant. So 5076 are the significant figures. The number 0.00345 has 3 significant figures. So the first non-zero digit in that number is the 3, the last non-zero digit is the 5, okay, and so all the digits between those are significant. So 3, 4, 5 are significant. Okay, so example 3, state the number of significant figures in each of the following. Okay, so in part A, the first non-zero digit is 1, the last non-zero digit is 3, and so these are the significant figures. So this has 3 sig figs. Okay. In part B, the first significant figure is 6, the first non-zero digit is 6, the last non-zero digit is 3, so even though it's a 0 in between there, that's okay. This also has 3 significant figures, or 3 sig figs for short. 0.47, the first non-zero digit is 4, the last non-zero digit is 7, and so there are 2 significant figures in that particular number. And then 0.007802, first non-zero digit is 7, the last non-zero digit is 2, everything in between there is significant, and so this has 4 sig figs. Okay, write the following numbers in scientific notation using 3 significant figures. Okay, so this involves 2 things. We're writing in scientific notation and we're also doing some rounding. So the first thing I'm going to do is round to the number of significant figures, and then I'm going to focus on writing in scientific notation. Okay. Alright, so this first number has 4 significant figures. So I first of all want to round it to 3 significant figures. So those are the first 3 significant figures. Like any rounding, if I'm rounding to, let's just do decimal places first. If this was 0.203500, those zeros are meaningless if it's a decimal, if it's a, if they're decimal places. If I wanted to round this to 3 decimal places, I would identify, right, those are my 3 decimal places that I need to keep. I look at the 4th decimal place and it tells me, in this instance, to round up. And so this becomes 0.204 to 3 decimal places. It's the same with significant figures, okay? So the significant figures are the 203. We look at the next significant figure, if there is another significant figure, to see whether or not we need to round up or down, okay? So that 5 or more tells me I need to round up. So my significant figures are going to round, so we're rounding, so it's approximately equal to, my significant figures are going to round to 204. Now, I'm not just rounding the number, 203,500 doesn't round to 204. So it means that every other digit now becomes 0. They still need to be there to hold the place value. We're not changing the place value of this 2. It's still a 100,000s digit. Okay, this is still a 10,000s digit. This is still a thousands digit. This is still a hundreds digit. You can't change the place value. Okay, so 203,500 rounds to 200 is approximately 204,000 to 3 significant figures. Okay, so now we want to express it in scientific notation. So we're going to take our 204, which are our significant figures. We're going to put the decimal place so that it is between 1 and 10, so it's going to be 2.04, and then we need to multiply by 1, 2, 3, 4, 5, 10, 5 times to make those the same thing. So 203,500 to 3 significant figures is approximately 2, and in scientific notation is approximately 2.04 times 10 to the power of 5. Okay, part B. Let's focus on the 3 significant figures first. So it has 4 significant figures. The first 3 significant figures are 5, 3, 8. We look at the next significant figure, which tells us that we don't need to round up or down at all. Okay, and so to 3 significant figures, this is 5,380. Okay, so if that was 5 or more, that pink digit, it would become 90. Okay, but it is not 5 or more, so it rounds to 80. You can think about it. 5,382 is closer to 5,380 than it is to 5,390. And it's nowhere near 538. So we don't just drop off the digit, we just replace the remaining, the figures that have been deemed non-significant by the fact we want to round to 3 significant figures, we just replace them with 0. Okay, so this number is approximately equal to 5,380, and now we want to write it in scientific notation. So that would be 5.38 times, we need to multiply by 10, 1, 2, 3 times, 10 to the power of 3. Okay, see, that already has 3 significant figures, so there's no need to do any rounding whatsoever. So this is actually going to be equal to, because we haven't needed to round off, it's going to be equal to 6.51. And then we need to divide by 10, 1, 2, 3, 4, 5, 6 times. So times 10 to the power of -6. Okay, this number has more than 3 significant figures. Those are the first 3 significant figures. We look to our 4th significant figure, which is not 5 or more, and so we don't need to round. Anything after, if we're trying to round to 4 significant figures, anything after the 4th significant figure is completely irrelevant. Okay, so what we don't do is we don't go, oh, that's a 7, so we round that up to a 5 and then we round the 8 up to a 9. That's not how rounding works. Okay, otherwise where do we stop? If you've got the number 0.4455555 to one decimal place, I look at the one decimal place, I look only at the second decimal place, it's not 5 or more, and so this to one decimal place is approximately 0.4. What I don't do is say, actually let's go a bit further down the track here. Okay, what I don't do is I don't say, okay, well, to one decimal place, all right, well that's not a 4, and that I don't round up because this is only 4, but this is only 4. Oh, but hang on, here's a 5 here, right down here. So that tells me to round this up to a 5, which means I round this up to a 5, which means I round this up to a 5. Otherwise, where do you stop? Unless you can see every digit, how do you know that somewhere down the track here there isn't a 5 that means that you round up? It's completely irrelevant. If you want to round something to one decimal place, the only digit that's relevant in terms of rounding is the second decimal place. Everything after that's ignored. Same with significant figures. If we want to round to 3 significant figures, we need to look at the 4th significant figure and the 4th significant figure only to decide whether or not we need to round up or down. Or, sorry, round up or not round at all. Well, I guess we are rounding down because we're dropping off some digits. So 0.00108, the 4 tells me I don't need to round up, so it stays 0.00108. So that's to 3 significant figures. It's approximately equal because I have rounded off, and now I'm going to write it in scientific notation, so 1.08, and then we're going to need to divide by 10 1, 2, 3 times, so times 10 to the negative 3. Okay, working with numbers in scientific notation requires the use of index laws if we don't want to have to expand them out and work with very large or very small numbers. So if I have two numbers in scientific notation being multiplied together, 2.1 times 10 to the 6 times 3 times 10 to the 7. Okay, rather than work out that this is 1 with 5 zeros and this is 3 with 7 zeros and then try and multiply those really big numbers together, I just think about working with the scientific notation. Now, these brackets are completely meaningless because the only operation in all of this is multiplication. Okay, so they're really just there to sort of define the two scientific notation numbers, but they're irrelevant. So I can do the multiplication in any order. So I'm going to do 2.1 times 3 and 10 to the power of 6 times 10 to the power of 7. So 2.1 times 3 is 6.3 multiplied by, we add powers when we're multiplying, 10 to the power of 6 plus 7 is 10 to the power of 13. Now, when you're working with numbers in scientific notation, combining them together in ways like this, you do need to think about making sure that your final answer is still in scientific notation, because the question specified that. So you do need to make sure that this number here is still between 1 and 10. So for example, if this had been 8.1, instead, in the original question, both the original numbers are in scientific notation, but this would have become 24.3, which means it's not between 1 and 10, and so we would have needed to make an adjustment. So you do just need to be a bit careful about making sure that your final answer is still in scientific notation. Okay, let's have a look at B. So if we've got 8 times 10 to the 9 divided by 4 times 10 to the 3, much like we did in our index laws examples in the previous videos, we can really just focus on the number parts and the power of 10 parts. 8 divided by 4 is 2. 10 to the 9 divided by 10 to the 3, we subtract the powers, that's 10 to the 6. 2 is between 1 and 10, so we're in scientific notation and all is good. Okay, here we've got 2 times 10 to the negative 1, all of that to the power of 5, over 4 times 10 to the negative 2, all of that to the power of 3. So let's focus on expanding out these brackets first. We've got multiplication, so we can just raise 2 to the power of 5 and 10 to the power of 10 to the negative 1 to the power of 5. So we're going to have 2 to the 5 is 32 times, or you could just write that as 2 to the 5 and keep things in index form if you need. 10 to the negative 1 to the power of 5 is 10 to the negative 5. And then over 4 cubed is 64 times 10 to the negative 2 to the power of 3, that is 10 to the negative 6. Okay, so 32 divided by 64, that's half, times 10 to the negative 5 divided by 10 to the negative 6. We subtract those powers. Negative 5 minus 6 is negative 5 plus 6, so that's 10 to the 1. Okay, let's focus on our scientific notation. Half is 0.5 times 10 to the 1. Now, this is not between 1 and 10, so I actually need to be able to write that as 5, okay? So that is the same as 5 times 10 to the negative 1. 5 divided by 10, essentially, okay? They are the same thing. And then we've got the 10 to the 1 here. So actually, really in scientific notation, this is just 5, technically, times 10 to the 0. So actually, it's a bit trivial in the end. The numbers didn't work out very nicely there. 5 times 10 to the 0, but really that's just 5. And we probably could have just got there from that point there. Okay, 5 times 10 to the negative 5 all squared. So that's going to be 5 squared, which is 25, times 10 to the negative 5 times 2, 10 to the negative 10. Now, once again, 25 is not between 1 and 10. So I need to write that as 2.5, and it's 2.5 times 10. So I'm not worried, I'm just focused on that, first of all. So that's 10 to the 1. They are the same thing. And then it's still times 10 to the negative 10. So now we combine together those powers of 10. So we've got 2.5 times 10 to the power of 1 plus negative 10 is negative 9. So that's our answer in scientific notation. Just to note, your CAS will sometimes resort to scientific notation when numbers are too long to be properly displayed on screen. We actually see it quite often in the graphing screen. And scientific calculators also do this. And so the screenshot opposite shows how the CAS displays numbers using scientific notation. So if you were to multiply together, depends a bit on my settings here, to multiply together two quite big decimal values, my CAS uses scientific notation to express it. It uses a little e, okay? And it's not broken, so you can see it over here. The number we've got there is 2.4478E8. We don't ever write that on paper. It's not maths, it's a CAS language or calculator language. As I said, scientific calculators do it in a similar way. So the way we would write this on paper, this means 2.4478 times 10 to the power of 8. That's the, I guess the little e might stand for exponent, but you have to understand that it's scientific notation, so it's a power of 10. So that's really what that number actually means. Hence, we're going to move this decimal point 8 places to the right. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So just being clear about what that means. There's no need to, if you want to type in a number in scientific notation, you just type in, 1.5 times 10 to the power of 8, whatever it might be. But if you see that little e in your CAS, and as I said, it comes up reasonably frequently on the graphing screen, just be aware of, that's just indicating that your number is either quite large or if you had a negative. So this one, for example, is 3.03324 times 10 to the negative 7, so that's a really small number. It's just a way of it, having a shorthand way to represent those really big numbers. Okay, so practice today in exercise 3G.